Hello, this is Mr. White, and this video is on implicit differentiation, part 3. Now, we've seen some interesting planar curves in our textbook, and we're going to be introduced to another one here in our first exercise of the video. And in the second exercise, we'll find out what the second derivative is of this implicitly defined function, and we'll also just briefly hint at what does the second derivative mean in terms of the shape of the curve that you see on the xy plane. Later on in the course, we'll really delve into second derivatives. But for now, let's get this out of here and take a look at this Cassini oval. We're going to find the slope of the tangent line to the graph at the indicated point of this curve, which is called a Cassini oval. And let me scroll down here first for a definition real quickly. You all know what an ellipse looks like. What you may or may not know is that its formal definition is that it's the set, it's a planar curve, and it's the set of all the points in the plane such that the sum of the distances to two fixed points, which are called the foci, plural of focus, is constant. We'll take a look at what that looks like in just a moment, but I want to immediately draw a contrast to how a Cassini oval is defined very similarly. But the big difference is that instead of the sum of the distances to two fixed points being constant, it'll be the product of the distances being constant. So let's see what all that means. Let me bring up GeoGebra here. And you see two fixed points along the x-axis, marked there with black x's there, at -3 and +3 along the x-axis. And notice that this magenta point up here, the sum of the distances to those 2 points is 10. In other words, this distance right here is 5, this distance right here is 5, they add up to 10. As I move along, let's move to about, let's say, around here. Notice that this distance is roughly 7, this distance is roughly 3. They add up to 10. Go to down here, notice that, let's say right about here. This distance is roughly 2, this distance is roughly 8. So you get the idea. The sum is 10 at all times, and it just turns out that when you find all the points for which the sum maintains 10, we trace out an oval or an ellipse. If I turn on a trace there, we see the ellipse being traced out. Okay, so that is an ellipse. In contrast, the Cassini oval has the constant, the product is constant. So once again, let's start with something like this. Notice that this point right here, that its distance from the 2 points is 3.1623 and 3.1623. And if you multiply those two numbers together, you get 10. Turns out that 3.1623 is about the square root of 10. If I go a little bit over, like, let's say right about here, I've got roughly 4 and roughly 2.5. Again, they multiply to 10, and so on. You get the idea. About 5, about 2. So they're maintaining a product this time of 10, and if I just find all the points that satisfy that, I am tracing out what's called a Cassini oval. Let's see what that looks like. Turn on the trace. And sort of a figure 8 there, except not meeting in the middle. That's a Cassini oval. All right, so that's the equation that you saw on the board a moment ago. Let's go back to that. And we're going to find, real quickly, we're going to find the slope at this point right here, at 4, 1. We're going to find the slope of the tangent line, of course, that red line right there at 4, 1. All right, let's get back up to the equation and get into the calculus. We are, of course, going to implicitly derive this. I will point out that when you take a close look at this equation, it wouldn't be too hard. The y only appears in one place. It's not scattered about the equation in multiple locations. So it really wouldn't be that hard to get this function written explicitly, to get the y all by itself. But I still would argue that it's easier to do this implicitly. So let's go ahead. Let's start by doing the derivative of both sides, d over dx of both sides. So d over dx of the left side, and whatever we do on the left side, we will do to the right side, of course. And let's just go through term by term. Now, notice there is going to be some chain rule taking place here. We've got all of this inside of a squaring function, right? So let's look at that squaring function as being the outer function. In other words, the blank parentheses inside of parentheses squared, that's going to be our outer function. And when I derive it, I'm going to get 2 blank to the 1 power. And then I'm going to focus on all the terms inside that are being plugged into that function. And I'm going to just write them here, x squared plus y squared plus 3 squared, which I'll go ahead and just write as 9. And then I'll multiply all that according to the chain rule by the derivative of these red terms. So the derivative of that would be 2x for the x squared, 2y dy over dx for the y squared, and then nothing for the 9. All right? Let's now derive the rest of the left side. Let's derive that. And that's fairly simple. That's 4 times 3 squared. That's just 36 times x squared. So this is 36x squared right here. And if I derive 36x squared, I get 72x. And on the right side, I'm taking the derivative of a constant. There are no x's or y's or any other variable there, so we will get 0 on the right side. Okay, our goal is to get that dy over dx by itself. We may ask the question, should we FOIL this out or not? See if you agree with me. I'm going to say let's not FOIL that out. Let's move the 72x over to the right. Let's add it over to the right side. And we'll get 72x. And as long as we're at it, let's go ahead and divide this over to the right side as well. So we move the 72x over, and then we'll divide by 2 quantity x squared plus y squared plus 9. And what I've got left is just this 2x plus 2y dy over dx. Let's reduce the fraction on the right. 72 over 2 will become a 36, right? So I'm going to have 36x over x squared plus y squared plus 9. And let's also subtract this 2x over. Let's subtract the 2x over. And we're left with 2y dy over dx. And finally, we'll divide by the 2y. We'll divide everything by 2y. So we'll get dy over dx equals 36x x squared plus y squared plus 9. And there's a 2y in the denominator because we divided by 2y. Minus 2x, which is also divided by 2y. I'm feeling a little off balance here. Let's just move that closer to the center. And finally, just to simplify that just a tiny bit more. Now we have a choice to make. Do we really want to simplify? How far do we go? Do we feel the need to combine this into a single term? Well, I'm going to remind you that our goal really was to just find the derivative at a single point. So technically, I could plug in that x and y value right now, right? I could have plugged it in a couple steps ago, perhaps. Or I guess no, I really had to wait until I got the dy over dx by itself. But anyway, let's just for the sake of good form, let's go ahead and simplify this a little bit, and then we'll plug in. 36 and 2, that'll give us an 18 up top. So we'll have an 18x over y x squared plus y squared plus 9 minus x over y, because these twos canceled out. And that was our derivative. Just to allude to something I just commented on, if we felt the need to take these two expressions, these two fractions here and do the common denominators thing, get them into one expression, you would come out with something that looks like this. Okay, I'll let you decide if you want to resolve that for yourself. Again, that's the type of thing where if you saw this in the back of the book, I would expect you to go a little bit further and try to match it. But again, that's not really our mission here. We are interested in this point 4, 1. So at the point 4, 1, let's go ahead and plug in. So x equals 4, y equals 1. That means that the derivative at that point will be 18 times 4. And let's go ahead and just calculate that. 18 times 4 is going to be 72. Over, our y value is 1, so we're plugging in a 1 there, and then a 4, and then a 1 there. So over, c, 1, I don't really have to write that, times parentheses, let's see, x squared plus y squared, that's going to be 16 plus 1 plus 9. That's going to be, see, 26. Let me just write 26. Minus x over y, or 4 over 1. All right, that's going to be, if I simplify that a little bit, that's going to be 36 over 13. I just reduced that first fraction there. And the second fraction I'll write with a common denominator. So instead of 4 over 1, I'll do 52 over 13. And 36 minus 52, let's see, that'll give us negative 16 over 13. So just to make a complete sentence here, I'll say at the point 4, 1, dy over dx equals negative 16 over 13. Put a box around it. And just to check, since we have the means to do so rather easily, on the calculator, negative 16 over 13 is about negative 1.23. If I go back to GeoGebra and I take a look at the equation for this tangent line, I see that the slope indeed is negative 1.23-ish. So we consider ourselves successfully done. All right, let's go on to the next one. Find the second derivative, d squared y over dx squared, in terms of x and y. This problem starts out pretty much the same as all other implicit differentiation problems. Let's do d over dx of both sides. And on the left, we'll get 2x for the x squared. And then we'll get 8y. And then according to the chain rule, dy over dx for the 4y squared. And on the right side, we'll get just 12 dy over dx. And with a little bit of luck, this is starting to become pretty comfortable for you by now. Let's proceed to find the dy over dx. Again, we ultimately want the second derivative, but we'll start by completely getting the first derivative solved and isolated. So let's get the dy over dx terms by themselves, or on the same side of the equation. Let's move this over to the right of the equal sign, and we'll get 2x equals 8y. And let's factor out the dy over dx at the same time. How about that? Plus 12 dy over dx. So again, 8y times the dy over dx gave us this term. And then 12 dy over dx gave us this term. Let's divide both sides by the 8y plus 12 in order to get dy over dx isolated. And let's just move the dy over dx to the other side as well. Let's write the dy over dx on this side, just since we're kind of used to seeing it on the left. And then on the right, we'll do the 2x over 8y plus 12. Notice that all of those terms are divisible by 2, so let's divide all three of them, that, and that, by 2, and get x over 4y plus 6. We're not done. As tempting as it is to put a box around it, we're not done. We need to derive that again. So let's, without further ado, do so. D over dx of this is going to be d over dx of this. And just because I'm super picky about such things, I suppose since I'm taking shortcuts, I really should write d over dx of that middle one too. And we will end up with, on the left-hand side, this is what's going to give us the second derivative. And we need to do the quotient rule on this. We have a quotient, no way around it. We need to do the quotient rule. So let's do the bottom times the derivative of the top. So bottom, 4y plus 6, times derivative of top, which is just 1. And I like to write the 1 just as a placeholder to say, look, I didn't forget to take the derivative, minus the top times the derivative of the bottom. So top, and then derivative of bottom is going to be just 4 dy over dx. Again, no derivative for that one, or the derivative is 0, I should say. All over the bottom squared, all over that squared. 4y plus 6 in parentheses squared. Now, I'm looking at all those even numbers in there, and I'm tempted to try to factor out some 2's, but I'm going to just make the judgment call that I'm going to proceed, and I'll worry about doing that later. If you wanted to do that right off the bat, you could. There's not a problem with that. Let's discuss what we're going to do next instead. Okay, so we're seeking this second derivative, and that's what we got on the left-hand side. But you notice what's not really acceptable on the right-hand side as far as a final answer goes? We should not have this dy over dx in our final answer. We really just want x's and y's in our final answer. So what do we do about it? Let's recall what we had just a step earlier. Remember earlier we solved for dy over dx, and we determined that it equaled x over 4y plus 6. So what we're going to do is we're going to substitute in. We're going to substitute in x over 4y plus 6 for this dy over dx. So let me shrink that down a little bit and rewrite 4y plus 6 minus x times 4, and I'm still running out of room. So excuse my shuffling here. I'm going to just clear up a little space here. All over 4y plus 6 squared. Okay, let's go ahead and plug in the dy over dx now. That's what's going right here, correct? So let's put in x over 4y plus 6. So we got a fraction within a fraction now, which we'll have to deal with, but at least we don't have the dy over dx in there anymore. All right, let's clean that up a little bit. So I have a fraction with a fraction. I'm going to try to look into my crystal ball a little bit and see what's up ahead. And I see that I have, due to that fraction within a fraction, I'm going to do a common denominator up there. So let's prepare for that. Let's do 4y plus 6. Let's put it in parentheses and leave ourselves some space. That's this 4y plus 6 right there. And leave ourselves some space and do minus 4x squared over 4y plus 6, all over 4y plus 6 squared. Let's go ahead and address why I left some space there. It's because I'm going to do a common denominator. So let's put 4y plus 6, 4y plus 6. All right, it's getting a little bit messy, but clouds should be parting here in just a moment. Should we distribute that? Should we FOIL that out or just call it 4y plus 6 squared in quantity squared? Let's be adventurous, and we often find that in the numerator it does pay to FOIL out because then you can get like terms and combine like terms and such. So let's take our chances. If I FOIL that out, I'm going to get 16y squared plus 24y plus another 24y So 48y plus 36. And then it's all over this 4y plus 6, as is this. So in that same numerator, let's go ahead and combine the numerators and do minus x squared, 4x squared, I should say. And that's all over this 4y plus 6 common denominator. Now, I could write all of that as a fraction over a big old fraction bar and put a 4y plus 6 quantity squared under that, but you've probably seen me doing this before if you've seen the previous videos. Let's instead multiply by the reciprocal of this. This is a comfort level of fractions that would be a big payoff if you can get used to this. 4y plus 6 squared. Okay, that's going to get around our fraction within a fraction. So it looks like we're nearing the end, and we are, but there's one really great trick that is coming up here that will complete our journey. Let's first combine any like terms. Let's see, there really aren't any, are there? So let's factor instead. Let's look for the greatest common factor up here. Looks like a 4, right? So let's take a 4 out of all of those. 4 times 4y squared, that'll give us the 16y squared, plus 12y, that'll give us the 48y, plus 9 minus x squared, and that's all over. Now let's be careful on the factoring down here. Let's keep in mind that what we essentially have down below is a 4y plus 6 quantity cubed there, right? So think of what 4y plus 6 quantity cubed is. It's really 2 times 2y plus 3, and then that's really being cubed, right? So again, you see the 4y plus 6 still being cubed. But let's go a step further. Instead of doing the cube around a big parentheses there, let's consider that it's 2 cubed times this quantity cubed, okay? You with me? Let's consider that as 2 cubed times 2y plus 3 quantity cubed. So I'll put the cube there and the cube there. And get rid of these parentheses now. And what I've really got is an 8 sitting right here. So I've got a 4 up top. I've got a 4 up top and then an 8 down below. I hope I'm not doing too much, and I hope I'm not completely losing you, but I also would like you to work on being able to handle these fractions efficiently and comfortably like this. So let's do one more simplification step before our big final step, and we'll have, let's see, 4y squared plus 12y plus 9 minus x squared. We'll have the 2y plus 3 on the bottom being cubed. And again, this 4 over 8 results, that reduces to just a 2 on the bottom here. All right, you ready for the big grand finale, the big dismount here? That looks like it could be done. It looks like we really can't do much further than that, but there is one last little trick. And that is to bring back the original equation. Here is the original equation that we started with. This is the original equation we started with. And do you see that present in our answer? It's in the numerator there, right? Let's rearrange that original equation and see what we can then do to really greatly simplify our numerator in our second derivative. Let's move everything to one side in that original equation. Let's keep the 12y over here, and let's add the 4y squared and subtract the x squared over so that we have just a 0 on the left. Okay, you buy that? Well, look at what we have in the numerator of our second derivative. We've got a 12y, which we had down here, plus 4y squared, and a minus x squared. And what does 12y plus 4y squared minus x squared equals? It equals 0. So that means that we can replace all of these 3 terms with 0. Pretty ingenious. If you're wondering how am I supposed to see that, how is I supposed to see that coming, it's a rare person that's going to see that unless they're shown, and you've just been shown, right? So let's write our final answer. All this disappears, and all we've got left up top is a 9 over 2 quantity 2y plus 3 cubed, and that was our second derivative. Put a box around it. And the last thing to do is take a look at what this graph looks like. And I said I was going to hint at what the second derivative tells us about a graph. So let's do that. Turns out that this graph is of a hyperbola. And let's take a look at what's, and notice that I have the second derivative calculated here. It'll dynamically update as I move this point along the curve. So just kind of observe what's happening to those values. Notice that along this upper branch of the curve, that that second derivative there is always positive. Notice that this value is always positive along this upper half, this upper branch of the curve. But notice that when I jump to the bottom branch, all of a sudden the second derivative is negative. So the second derivative isn't telling us about increasing or decreasing. We see that even during the increasing parts right now and the decreasing parts, the second derivative remains negative. Turns out what the second derivative tells us about is whether the curve is essentially smiling or frowning, I'll say, in layman's term. Notice on the upper branch, we might say this is more of a smiling shape. And notice that the second derivative is positive. Whereas on the lower branch, we see more of a frown shape, and the second derivative is negative. Also notice that where the curve, where the frown is the strongest, right in the middle, that the second derivative is at its most negative. And when the curve flattens out and becomes kind of linear in shape, it's roughly linear along this stretch, notice that the second derivative is really close to 0. So there's your hint, is the second derivative. Later on, we'll come up with more official sounding words like concave up along here and concave down along here. But that's enough for now.